So good afternoon. It's good to be beyond lunch this morning. So I'm going to talk today about quantum and our open hardware innovation. I mentioned it in a talk just before lunch. For those that missed it, I'll do a very short recap of that and then get into some more details on it. So, our journey first, Microsoft's journey in open hardware innovation. We joined the Open Compute Foundation exactly 10 years ago in 2014. Since 2014, systematically made contributions towards standardization and interoperability of infrastructure. Every year, I put some of the major milestones on this little timeline at the bottom. It doesn't include everything. Some of those major milestones were Project Olympus in 2016, Project Cerberus in 2017. And Project Cerberus was a security chip that we implemented for attestation and secure boot of devices that didn't have those security properties. And then if we fast forward through to 2022, we formed a consortium with Google, AMD, and NVIDIA to develop Calyptra. And security experts from those companies came together, and we developed Project Calyptra together. And that's shipped. It's reached its 1.0 milestone. It's getting built into products and is out there. And then in 2023, we worked with OCP and others in the industry on OCP Safe, which is a framework for security audits on devices to ensure they conform to the OCP security requirements. So when we look ahead, beyond that previous timeline at what the next chapter is for open hardware innovation, we usually use technology trends to give us indicators on what that's going to be. It's not a complete blank slate. We look at emerging technologies and how they're going to influence future infrastructure. In fact, I work in Microsoft for Azure, and I manage an architecture team that's responsible for next generation hardware. This is generally how we think about where innovations are going to come from, what's the next generation technology that we should be mapping. And I mentioned this earlier in the talk, so I won't repeat it, but confidential compute, we see that as a big trend. A lot of workloads in cloud are shifting towards confidential compute, and confidential compute is about the isolation of sensitive workloads and hardware attested and protected trusted execution environments. So they're protected during use and as well as at rest and in transit. So that's what confidential compute is. Generative AI, I talked about that. That's a major trend, of course. We're seeing that everywhere. And then this other one I put in here was quantum resilient cryptography, and that's what the focus of the talk today is going to be on, is quantum computing. We're seeing generative AI and the influence from generative AI really advance science, and advance science faster than we would have anticipated 2-3 years ago. So this is the runway that we have for quantum computing is actually becoming shorter, and the urgency is becoming greater to adopt quantum resilient cryptography. And this will be disruptive. The security protocols involving asymmetric key exchange, they're all going to be impacted by quantum computers. And there are new standards for quantum resilient cryptography. Those standards are still emerging and getting published, but we're running in parallel with those to get implementations out there. Then, of course, I spoke earlier about physical infrastructure and composable architectures, but as I said, the focus here is going to be on the quantum resilient cryptography. So quantum as a sphere of influence shouldn't be underestimated. if you're developing hardware or designing ASICs today, and you're not already planning quantum intercept, you're likely already late to the game. In fact, the advancements we're seeing in quantum is coming through AI. I mentioned in a talk earlier that Azure has a co-pilot for quantum to help people reason about complex chemistry, material science problems. We've also published some advancements with qubit reliability. It's a major step forward in being able to scale quantum computers, is getting reliable qubits. So with quantum, the integrity of protocols today, TLS, is going to be impacted, which is widely used for HTTPS. All of the attestation protocols for confidential compute and attestation protocols that we know of today, key release, key exchange protocols, they all rely on asymmetric cryptography, which is impacted by a powerful enough quantum computer. And NIST, the national NIST has published specifications, early draft specifications for the algorithms in quantum computing, and for quantum cryptography, I should say. And those publications, although not finalized, we're using those as a guideline and following them quite closely as we implement, just like we did with Calyptra in 2022, implementing an open source silicon hardware accelerator for quantum cryptography. And we call that accelerator the Atoms Bridge Accelerator. And it's going to come in different forms that I'll talk a little bit about later on. But the urgency behind getting this accelerator out there is when we look back at how security has gone with traditional infrastructure. We have challenges with hardware timelines. If capabilities are missed in a platform, it's typically 18 to 24 months before the next product is out there. And from a silicon manufacturer's point of view, the products they're making today, they will ship in 2 years' time, and then they expect those to live on for maybe another 2-3 years past that. That's right in the quantum era. That's the urgency with Atoms Bridge that we're trying to portray, that we don't have time. In addition, the complexity, the previous classical algorithms, asymmetric algorithms, they were single points on an elliptic curve, and the complexity was relatively low. Still, we saw a lot of fragmentation. We've seen a lot of issues with implementations on those. Side channels is a whole other area of research that's still going on in with those protocols. And then the fragmentation of security features and implementations in hardware has plagued the hardware industry. And how we dealt with that in classical infrastructure, we can look at how we dealt with it in the past. What Microsoft would do with OCP, and put requirements in OCP, and also have our own requirements that may be built on top of OCP. We would provide those to suppliers like hardware manufacturers and system manufacturers, OEMs, ODMs. We provide these security requirements and request that these suppliers adhere to it. And what we would get back is specification-driven security interfaces from these suppliers. It was sometimes custom, sometimes maybe it wasn't implemented correctly. But certainly fragmentation, even when it was, just nuanced differences in it, always cause problems at higher levels as we go to deploy security services in the cloud. What we would do when we get these systems back is we would audit them for conformance. This all took time. We would audit them, see if they comply with security requirements. If they did, then great, we could go use them. If they didn't, we would solder on a security chip. A security chip was called Cerberus, and we published that in 2016, and we've used the Cerberus chip in our infrastructure for about 10 years. So for the past 10 years, when systems would come in, they didn't comply with security, we'd bolt on a security chip that forced those security requirements. It wasn't easy. It's not an easy undertaking to interpose a security chip on an ASIC that's designed with fragile security or with no security. But these are the steps that we undertook. And we weren't alone in this journey. Other CSPs did the very same, other cloud service providers and hyperscalers, they did the very same thing, and during the same era. Like Google's been very open with their Titan security chip, and it's following the same process. Does the system comply with security requirements? No. Okay, we would go and bolt on a security chip that gave it some security. So the challenges with this, of course, this method is when we're looking through the lens of AI and the trajectory for infrastructure scaling beyond sizes that are previously imaginable. Just the pace at which things need to move, that soldering on or this bolting on of a security chip to give an SoC some security isn't going to work. We also see architectures becoming highly disaggregated, and that's pretty disruptive. When you would have single systems, it was easy to put security chips into single systems and reason about the boundary of a system and having a platform level security chip that enforce security throughout. When we have disaggregated architectures, the system itself and the boundary of the system can become logical in the data center. So that's a big challenge. And then the other one is the big shift that we see towards confidential compute. These platform rooted trusts aren't generally exposed to the workloads that are running on the infrastructure. Instead, those workloads would rely on the cloud service provider for providing that security. With confidential compute, the workload or the tenant that is running that workload, they get the security assurances from the hardware directly and don't have to rely on the CSP for the cloud service provider for those security assurances. So that led us in 2022 to the creation of Calyptra with the others I mentioned earlier. And Calyptra is an open source silicon rooted trust in the form of a reusable block designed for ease of integration into SoCs. And what Calyptra does is it provides transparency and consistency of the rooted trust mechanism. Calyptra 1.0 is already shipped and is arriving in many SoCs. So we're looking forward to those reaching the market. The rooted trust is an important element in secure devices because it anchors the chain of trust in hardware and provides a set of foundational security properties that underpin the integrity of higher level security features. This is a very critical component. And that foundation gives applications and workloads integrity assurances of the underlying hardware. Calyptra and the V1 version of Calyptra that has shipped, it met all CNSA security requirements. It even has inside in it, it's got asymmetric cryptography, of course, but it also has hash-based signatures. And at its core, what Calyptra does is it's a rooted trust that takes cryptographic measurements of an SoC security state. These measurements, along with Calyptra's endorsement, that are then used for verifying the trustworthiness of the SoC. But we didn't stop there. As we look now at this quantum era, what are we going to do? That's where we have this Adams Bridge accelerator. And the Adams Bridge is an additional accelerator that will add to Calyptra to accelerate quantum cryptography. And that will get right to the root of identity and all of the other security services that Calyptra provides. Now, the Adams Bridge itself is it comes in both an embedded version of the accelerator that goes into small embedded devices like Calyptra, or small embedded security controllers like Calyptra. It's got that low power quantum crypto engine. It's also scalable and can be used embedded or standalone. For higher performance, a standalone engine will help with things like TLS offload and accelerating other security protocols that rely on asymmetric cryptography today. They'll be able to take advantage of this Adams Bridge standalone accelerator in addition to getting it out of the box in Calyptra. And that's really the ecosystem enablement for it. It builds with Calyptra, it's composed with Calyptra, or it can be composed independently for use in a larger accelerator beyond the root of trust scenarios. The Adams Bridge artifacts, how does it come? So there's 3 key components to Adams Bridge, and it very much follows the Calyptra playbook. So we have a set of specifications that describe the Adams Bridge architecture and the Adams Bridge integration into Calyptra and secure devices. We have the RTL, or Register Transfer Level language, that composes Adams Bridge and forms that reusable silicon block inside in Calyptra. And then we have the drivers and the firmware for Adams Bridge that are written entirely in Rust and get measured by Calyptra. And then how you can get involved with Adams Bridge. As I said, it follows Calyptra's playbook. It's been run through the Calyptra consortium. Specifications for Adams Bridge along with Calyptra will be made available through Open Compute. The RTL, just like Calyptra today, is made available through CHIPS Alliance. And then OCP and the CHIPS Alliance in collaboration with the Linux Foundation are working to serve the needs of both communities, where you can have specifications available through OCP and then source code managed in CHIPS Alliance. And to get involved with Adams Bridge or with Calyptra, I would encourage you to reach out maybe to any of the Calyptra team that are here from AMD, Google, Microsoft, or NVIDIA, or go out to calyptra.io, and you'll see that there are specifications already available around Adams Bridge, and that RTL will be released shortly. It's still been worked on by the team. And out on the Calyptra website, there are ways to get involved with the in the Slack channel and the mailing lists for Calyptra. And you're free to ask questions there on Adams Bridge, as it's the same team delivering the technology. So with that, I will take any questions folks might have. Because that's me. Do we have any questions? Quantum, it's easy. Yeah. All right, thank you very much.